While NASA flies the International Space Station some 240 miles above Earth, it is also operating a mission 63 feet below the surface of the Atlantic Ocean. NEEMO is the NASA Extreme Environment Mission Operations Program, and it has its 16th crew on board the Aquarius research habitat off the coast of Key Largo, Florida right now. This time they're simulating a visit to an asteroid, building on lessons learned from NEEMO 15 to test solutions to the engineering challenges that'll be faced on such a mission. One member of NEEMO 15 is also on NEEMO 16, and he's with us now to provide an update on the mission. Dr. Steve Squyres is a professor of astronomy at Cornell University, is chairman of the NASA Advisory Council, and is also principal investigator for the science payloads on the Mars exploration rovers. Steve, since we can see you, would you explain where you are in the habitat and tell us how much space there is to accommodate you and your crewmates?
Sure, I'd be glad to. Right now I'm in what we call the main lock. This is kind of our primary area for any kind of group activities, eating, food preparation, that sort of stuff. This is where we have our daily briefings and that kind of thing. Aquarius is a pretty cozy place. It's roughly the size of a school bus, maybe even a little smaller than that. 6 people in here for 2 weeks. We get to know each other pretty well. So it's a small volume, but it's certainly more than adequate for what we're doing down here.
I mentioned that this mission is intended to simulate a visit to an asteroid. For starters, is the size of the habitat and the isolation important to that simulation?
Yeah, I think it is important in that simulation. When a crew goes to an asteroid, it's going to be a small vehicle. They're going to be in tight quarters, maybe even tighter than what we're in here. And yeah, the isolation is a big part of it. We're doing most of this mission with a 50-second time delay between us and mission control. When a crew goes to an asteroid, they're going to be so far from Earth that it might take 10, 20, 50, 60 seconds for a radio signal traveling at the speed of light to get to that asteroid and to that crew, and then a comparable time to get back. And so we're simulating that, and that does provide a real sense of isolation while we're down here.
Now, that communications delay is one of the primary things that you folks are looking at here. Is a 50-second communications delay, is that what you've been working on throughout?
Yeah, we've been using 50 seconds for almost all of the mission. We had one day where we were doing some emergency scenarios where we would have a simulated emergency on board, a need to interact with, say, a doctor, a flight surgeon on the ground. And for some of those, one of those we did a 5-minute time delay, and one of those we did a 10-minute time delay. And it really isolates you. You know, if you've got a very dynamic emergency situation going on, and you try to talk to mission control, and you get an answer back 20 minutes later, you're basically on your own.
Well, I was wondering, have you found that you've changed how you talk to mission control because of those delays, and the way they talk to you?
It has changed things. Yeah, it has changed things quite a bit. When you are talking to them, typically what you'll do is you'll say, Mission Control, this is Aquarius, we'll have a message coming to you in 10 seconds. That way they've got 10 seconds to kind of get ready, get a heads up, know that a message is coming. We find ourselves using text a lot. Texting is a good way to communicate back and forth when you have a time delay. It's very much like texting in any other setting. So yeah, our interactions with mission control are different. They're also more limited. There's not as much back and forth because, again, if we're doing a simulated spacewalk, which is a pretty dynamic thing, rather than them sort of talking to us constantly as we're doing the job, most of the communications is just within those of us down here, the crew members who are outside, crew member who was inside the habitat.
You find you take things upon yourselves more rather than asking for permission or help.
Yeah, and it simply becomes necessary to take more initiative, and I think that's very representative of what's going to happen to a crew that goes to an asteroid, a crew that goes to Mars. Anybody who goes far from home, you're going to be much more. You're going to have to be much more independent.
The communications delays, as well as the crew size, are two of the main areas of focus for your mission. The third one is restraint and translation techniques. Can you tell me why that's applicable, particularly to an asteroid mission?
You know, honestly, I think that's the most important, most crucial thing that we're doing down here. When you get to an asteroid, you're going to be going to an object that's small. I mean, most of the asteroids that we're talking about sending crews to are at most a kilometer or two inside. They're little size. They're little objects. What that means is they effectively have no gravity. So you're doing a spacewalk. You're in zero G when you're interacting with these things. Now, we have lots of experience with crew members doing spacewalks, for example, outside the International Space Station, but asteroids don't have handrails. Asteroids are bumpy, irregular, unpredictable surfaces, and so how you do scientific exploration in zero G on the surface of an asteroid is something that no one knows how to do. And really what this mission is about primarily is learning how to do that. And so we're trying a whole bunch of different techniques for moving, for anchoring ourselves, for moving around once we're anchored down onto the surface, positioning ourselves, things that we call worksite stabilization, getting into a stable environment where you can interact with the surface. We're trying out a bunch of those techniques to see what works well and what doesn't.
Can you give me a few examples of what you've been doing out there? How you've been trying to simulate that?
Sure. One thing that we assume, and we don't know how this is going to actually happen, but we'll assume that some kind of anchoring technique can be developed where you can fasten something solidly to the asteroid surface. So then imagine if you've got a couple of anchor points, you can string a line, effectively a tight rope, between them. We call that a translation line, and you can move over hand, you can tether yourself to it to keep yourself safely in place. And so that's an example of one kind of translation technique that we would use.
Now, those things have been done on space station before and on space shuttle, but translating along that line. But we haven't had to.
In some ways, the difference is you have to put that line in place yourself because the asteroid doesn't provide it for you. Another thing that we're using are what we call jet packs, but basically it's a back-mounted thruster package that you can use to translate, that you can use to fly around. Those are great for covering long distances very, very quickly. Very, very good. But of course, once you get to a work site, you've got no way to stabilize yourself. If you hit a rock with a hammer, you're just going to go drifting off into space. One that we all like very much is we have these small submarines down here, one-person submarines, and what those do is they simulate a small space exploration vehicle that you can take with you to an asteroid. And you can use those to position what's called a foot restraint. This is something you can clip your feet into, gives you a solid, stable platform. The submarine will take you to the position you want to be at, will settle into a stable configuration. You clip your feet into this foot restraint, you got both hands free, and then you just go to work. And that's turned out to be a very effective technique.
I would imagine that the difficulty comes in making the submarine hold its position then.
Yeah, having the submarine hold its position would be the hard part. The way you would do that in space is you would do it with a position and hold capability on the attitude control system on the spacecraft. So it's using thrusters to stabilize itself and keep itself solidly in place. The way we do it, the way we simulate that with the submarines is they just simply settle down onto the bottom.
And you hope that you can count on that on the asteroid?
Well, you're not going to be able to settle down onto the asteroid. The asteroid doesn't have gravity to hold you in place. So when you get to the asteroid, you're going to have to depend on the spacecraft to be able to position itself and hold itself in place. And so now we've got a set of specific requirements that we can give to engineers and say, okay, we need a spacecraft that can do this.
We haven't mentioned it specifically, but I assume that you're going outside on dives to simulate the working in weightlessness.
Yeah, that's correct. So we're doing simulated spacewalks. As we speak right now, there's one underway. I don't know, maybe you can even hear it in the background. Kimia Yui and Dottie Metcalf-Lindenberger are outside simulating a spacewalk right now while I'm talking to you. We do 2 simulated spacewalks per day. We send 2 crew members out at a time, typically for about 3.5 hours. So we do 1 pair out in the morning, 1 pair out in the afternoon.
I mentioned that you were a member of the previous NEEMO crew. Can you give me a sense of how some of the lessons that you and your previous crewmates learned are being explored or examined or exploited on this mission?
Yeah, we learned an enormous amount on NEEMO 15, my previous experience down here, and that has all been put into action on NEEMO 16. On NEEMO 15, for example, we did have translation lines, but they were little flimsy things. Imagine a clothesline kind of thing, and they were floppy, and you couldn't really stabilize off of them. It wasn't a good way to move to stabilize yourself once you moved around. So, lesson learned from that one, we've got basically really tightly tensioned climbing ropes, effectively, that we can use to move around, and those are far superior to what we used on NEEMO 15. The tools for collecting samples are all better. Great deal that we learned. Now, the other thing that happened on NEEMO 15 is NEEMO 15 we had a hurricane. A hurricane came through, and a mission that was supposed to be 12 or 13 days long got cut short after just 6 days. So on NEEMO 15, we never got to even try out the submarine stuff, and so that's been a big lesson learned on this mission, is the value of working with those small spacecraft that are simulated by the submarines.
On the subject of submarines, you had a blog post that you just published about your work with submarines. NEEMO 16 has been making a big effort with a lot of different social media outlets and live video streams to share the mission with people. How did the submission go yesterday, or 2 days ago?
I think, I think yesterday and the day before, I got to do NEEMO 15, NEEMO 16. I think the past 2 days have been the best 2 days of NEEMO that I've ever experienced. One of our habitat technicians down here is James Talasek. James is an incredibly experienced diver. He's got 20 years of professional dive experience, 12 years down here at Aquarius. He said that yesterday was the most complicated thing he's ever seen anybody try to do in the water. We had 2 submarines in the water. We had 2 aquanauts out on jetpacks. We had, at some point, 9, 10, 11 different support divers in the water, managing tetherers, managing umbilicals, and we just nailed it. Everything went right. We got everything done. We collected all the data. I think we've definitively shown how well that combination of submarines and jetpacks works. It's been just a fantastic mission, and the last 2 days in particular have just been, for me, the high point of both of my NEEMO missions together.
What's left on the agenda for this flight? What else do you folks have to do before you come up at the end of the week?
Well, we've got 2 more days worth of EVAs, today and tomorrow, 2 more days of simulated spacewalks. And the nice thing is, at this point, we've learned so much that now we can try other things that we might not have thought of before. I wouldn't call it quite improvisation, but it's experimentation. Before we came down here, we had a set of specific tasks that we wanted to achieve. We've really achieved most of those. And so now we've got time in the schedule to build on what we've learned, try some new things, try different techniques, using them together in combination in ways that we might not have thought of previously. Experiment, take advantage of the opportunity. We're down here, we've got everything dialed in, we've really found the groove, we know what we're doing it well, and so now we can try a bunch of different things and see what works.
You're already implementing some of the lessons you've learned here.
Exactly.
Before this is even over. Well, Steve, good luck with the rest of the mission. We appreciate your taking a few minutes to bring us up to speed on what's going on.
Thanks very much. Enjoyed doing it.
NEEMO 16 crew member Dr. Steve Squyres of Cornell University. And you can find out a lot more about what Steve and his crewmates have been doing on the floor of the Atlantic Ocean. They have blog posts and pictures, the whole thing. You can check it out on their website at nasa.gov/NEEMO.